Hello there, geometers, inquisitive little geometers. This is chapter dos, section uno. Welcome to chapter 2. This whole chapter is about reasoning and proof, and it will get a little more complicated as we progress in the chapter, but right now it's actually pretty easy. We are talking about inductive reasoning and conjecture. Those are just some really fancy words for basically observing a pattern. That's inductive reasoning, is basically observing a pattern. And a conjecture is making an assumption based on the pattern that you're observing. For example, this might seem like a little strange example for you, but for example, let's suppose that you meet a guy, ladies out there, you meet a guy, and you find out that this guy starts dating somebody, a girl, and he dates her for like 2 weeks and then he dumps her. Okay, whatever, you move on. So then you find out that then he starts dating another girl. And then he dates her for a couple weeks and then he dumps her. And then he starts dating another girl. And he starts dating her for like 2 weeks and then he dumps her. So you can start trying to see if there's a pattern, and we probably don't want to date this guy, right? I hope, okay. Because most likely what's going to happen is when you start dating him, he's going to dump you after 2 weeks. Okay, that's the pattern that you're observing. And we observe patterns all the time. It doesn't have to be math related. And once we make an assumption based on that observed pattern, like we might assume, for example, that said guy is a player, because that's what we're observing. That's called a conjecture. So now we're going to apply this whole thing to an example that's more math related. Sorry, we can't stay with boyfriends and girlfriends all day. But here it is, example 1. Write a conjecture that describes the pattern in each sequence. Then use your conjecture to find the next item in the sequence. So our first option here is movie show times. We have show times at 8:30 a.m., the next one's 9:45 a.m., 11 o'clock a.m., and then 12:15 p.m. So what we can observe from this, if you haven't already seen it right now, I'm going to help you out here, is that there is an hour and 15 minutes of time that is elapsed between the two show times. So from 8:30 to 9:30 would be an hour, and then 15 more minutes, 9:45. From 9:45 to 10:45 would be an hour, and then 15 more minutes would be 11. So that is consistent with 1 hour, 15 minutes. And then we have from 11 to 12:15, which is also 1 hour and 15 minutes. So we're observing a pattern that a movie starts every hour and 15 minutes. So based on that conjecture, we can write that out. But basically what we want to write out, I'm not going to write it on here because there's not enough space, but what you want to say as far as writing your conjecture is that it appears that a movie starts every hour and 15 minutes. And then it wants us to use that conjecture to find the next time that there'll be a movie. So 12:15, we want to add an hour and 15 minutes to that. So 1 hour would be 1:15. So the next movie show time would be 1:30 p.m. if it followed the pattern. So there you go. In part B, same idea but a different type of problem. We have diagrams now. And you see that this number here correlates to like how many sides are in the figure. And that side, this little guy has 4. And then you can see here that they're adding like a double square, if you will. But now as you count the segments, there's, you know, the original 4. And then you have 5, 6, 7, 8, 9, 10. So there's a 10. And then you add another segment, and when you count all the segments, there's 18. You add another piece, and you count 28. Add another piece, and you count 40. So now what we need to do is kind of see what the pattern here is. So we're going to look at the numbers themselves. From 4 to 10, that is a 6 unit difference. 10 minus 4 is 6. And then here from 10 to 18, that's an 8 unit difference. And then from 18 to 28, you have a 10 unit difference. And then from 28 to 40, you have, what, 12? So, I can't draw my little arrow, but 12. So, as we look at the pattern, it appears that every time that we add a figure, we're increasing the difference between the two by 2. So it was 6, and then it was 8. 8 and 2 is 10. 10 and 2 is 12. So if we use that conjecture to find the next item, we would expect it to increase by 14, because 14 is 12 plus 2. So it would have 40 plus 14, so it would have 54 segments. And you could draw that, you could add, you know, your little extra piece there, and you could count them all out. But it would be easier to just use the numbers and go with 54 segments. So now we're going to try your hand at observing some patterns. We have 3 different scenarios here, and then using that conjecture to actually predict what the next item will be. All right? And then we have example 2, and it says, make a conjecture about each value or geometric relationship. List or draw some examples that support your conjecture. So what's happening in this case is that we don't have the actual numbers to work with or the diagrams to work with. They want us to do that. So for part A, it says the sum of 2 odd numbers. So what would happen if you had 2 random odd numbers and you added them together? So what they want us to do is to provide some examples to support what our conjecture would be. I don't know if you already have a conjecture, but I'm going to pretend that I don't, because I kind of already do. But I'm going to pick 2 odd numbers like 1 and 3, or 37 and 5, maybe, I don't know, 13 and 21. These are all odd numbers. And I'm just picking random numbers to just show you that it doesn't have to be something that you're like, it has to be a certain order. I can just pick any odd numbers and add them together, and then I should see a pattern. 1 plus 3 is 4. 37 plus 5 is 42. And 13 plus 21 is going to be 34. Okay? So again, I don't know if you've seen the pattern yet, but what I'm seeing is that whenever I add 2 odd numbers, I end up with an even number. So that would be my conjecture, is that the sum of 2 odd numbers is always an even number, which makes sense because when you have an oddball, basically what it means to be an oddball is that everybody has a partner and you're like the third wheel. So what happens when you have 2 groups that have an oddball is that those 2 oddballs can actually pair up and be a group. And that's what's happening here, is that this oddball is pairing up with the oddball from here and creating an even number. So that is going to be part A, and those are my examples that I have right there. In part B, it says segments joining opposite vertices of a rectangle. They want us to make a conjecture about that. So what you want to do is start off by drawing a series of different rectangles. So I can make one like this. It doesn't really say how many examples you have to have, but I'm just going to put maybe 3. And I'm just drawing some different sized rectangles. And you could probably use a ruler, it'd probably be better. But segments that are joining opposite vertices. So here's a vertex, and let's go to the opposite vertex. And then so this is what we're looking at. We're looking at this segment and that segment. What do we seem to observe as we draw these vertices? And again, I don't have a ruler, so my segments aren't as straight or accurate as yours could be. I would encourage you to actually use a ruler and make them more accurate. But what I can tell by looking at these is that the segments that join opposite vertices appear to be congruent. They appear to be the same length. And what you could do is to test that is you could actually grab a straight edge or a ruler. It doesn't really matter what units you're using, but you can actually like measure. And like on my ruler, for example, I'm doing inches here. This is 12 inches, 13, 14, 15, 16, 17, 18. It's roughly 18. It's a little over 18. And then if I go the other direction, I also get the same thing, a little over 18. So you can use that to measure the actual segments to confirm that in fact the vertices, the segments joining opposite vertices of a rectangle are in fact congruent or equal. So that would be my conjecture and my drawings that are supporting my conjecture. So that's example 2. And now you can try your hand at these 3 examples. And then we will move on. And here we have example 3 and do-it-yourself number 3. And as you can see, the board says, we'll be done in class. It had some crazy graphs going on and charts that I just didn't think I would want to spend time drawing on my board. But we will do that in class. So you can leave some space in your notes for this guy, and we'll do that in class. And then we're going to go to our last example, one of my favorites, and that is counterexample. I always love this because if you read the directions, it says, find a counterexample to show that each conjecture is false. So a lot of times I get students that say, oh, but it's true. No. The directions say, find a counter to show that each conjecture is false. We know, right now, I am telling you, each one of these statements is false. I don't care if you think it's true, it sounds true, it might be true. It's not true. It's false. Your job is to find A counterexample. And a counterexample is basically an example that shows that what the statement is saying is not true. So it says here, if n is a real number, then n squared is greater than n. Well, I can think of a couple of examples that would work for that. What if n was negative 1? What if n was 0? What if n was 1? Okay? If n is negative 1, then what I'm trying to say here is that negative 1 squared is greater than negative 1. I'm replacing the n with negative 1. So negative 1 squared is positive 1. And is 1 bigger than negative 1? Absolutely. So you're thinking, see, I told you it's true. But it's not true for any real number. It's only true for some real numbers. What if I had 0? 0 squared is greater than 0. Is 0 bigger than 0? No, 0 is not bigger than itself. Okay? Bigger, it's not saying equal to, it says it has to be bigger than. So this is false. Okay? No, 0 is not bigger than 0. And the same thing happens here. What about 1 squared is greater than 1? Is 1 bigger than 1? No, 1 is equal to 1, but it's not bigger than 1. So there's two examples that show that this is not a true statement. So that's your job, is to find an example that shows that the statement is not true. Do not sit there and try to convince yourself that it is true. It is not true. So part B says, if JK equals KL, then K is the midpoint of JL. And this sounds very true. In fact, I can draw you some examples of how it is true. I can draw a segment, and that's what they're playing on. They're playing on you not reading into the problem. You always have to think tricky. You always have to think tricky, okay, when you come to these little guys. So, of course, you start thinking about the obvious. JK equals KL. So if I call this J, and this K, and this L, then yes, indeed, if JK is the same as KL, then K is the middle of JL. Perfect. But it never said that the points had to be in a straight line. So what if I drew myself a different diagram, like so, and like so, and like so. And you're going to be, oh, but that doesn't count, Mrs. Martinez. Yeah, it does. As long as I follow what it says. It didn't say that JK had to, that JL had to be a straight line. So I could call this JKL. And I could say that JK is congruent to KL. Totally, totally, totally. It satisfies what the thing says. JK is equal to KL. Does that imply that K is the middle of JL? Clearly not, because K is not even on JL. Okay, so this is an example, a counterexample that shows that this is not necessarily true. Now, if they had said that JL was a, were all collinear points, then that would be a different story. But it did not say that, so therefore this statement is falso. So now you will try some counterexamples of your own. And once you've done that, you will have completed your notes for this lesson. And I will see you in class. And gracias for watching.